When it comes to performance, an engine is only as good as the air it breathes. In the field or on the job site, engines live in a hostile atmosphere of dirt, dust, sand, and chaff. Successful preventive maintenance starts with stopping these contaminants before they wear away power and profit. The more air you can put into an engine cylinder, the more power it develops. Traditionally, adding more air meant adding cubic inch displacement with a larger cylinder and piston, like this. But as power goes up, the size and weight of the engine finally becomes impractical. The modern way to add more air is to turbocharge the engine. A turbocharger is simply a blower that rams more air into the cylinder by compressing it. The more air is compressed, the hotter it becomes. On more powerful engines, we add an intercooler to cool the air. Now we can pack a tremendous volume of air into the cylinder without increasing engine size. A naturally aspirated engine consumes about 13,000 gallons of air for every gallon of fuel. A turbocharged engine uses even more air. And on more powerful intercooled engines, air consumption is still greater. The air we breathe is free, but the free air an engine breathes can be very costly. The more air an engine takes in, the more work the induction system must do to keep contaminants out. The typical modern air induction system, equipped with a dry air cleaner, is designed to provide air in the right quantity and quality. The system consists of the pre-screener and pre-cleaner. Intake air then moves to a primary element, usually the final barrier to particles not removed by pre-cleaning. Many induction systems include a safety element to prevent serious engine damage should the primary element fail. The system directs air to the intake manifold or turbocharger through pipes and connectors, which seal the clean processed air from dirty outside air. The equipment and its application influences the location of the point where air enters the intake system. When a vertical stack is used, it is positioned carefully to avoid drawing exhaust fumes and is protected from rain. The pre-screener is a simple device to prevent leaves, chaff, lint, and other large contaminants from entering the pre-cleaner and air cleaner. On a vertical stack, it's usually part of the pre-cleaner or rain cap. A pre-cleaner is required to filter out larger dirt particles before they reach the primary element. Otherwise, the primary would have to be unreasonably large in size, and it would require servicing too often. When the air intake is located under the hood, pre-screening of lint, chaff, and leaves is usually accomplished by the grill screen. It is important that this screen be in place at all times. Pre-cleaners mounted behind the grill screen may be an integral part of the air cleaner canister. Dirt separated by the pre-cleaner is discharged at a rubber unloader valve or trapped in a collector bowl, which is periodically emptied. This type directs the dust to the muffler, where it is expelled with the exhaust. Pre-cleaners will remove from 80 to 90% of all contaminants before they reach the primary element. But what gets by can rapidly destroy an engine unless it is completely eliminated. And this is what gets by the pre-cleaner: a fine powdery dust, very much like talcum powder. It feels smooth to the touch, but engines are machined to such close tolerances that these dust particles will destroy them. Now, mix a bit of this silken powder with some engine oil. It feels slick, almost like a lubricant. Now, let's rub the glass with a piece of metal and see what happens. In just a few seconds, the erosive wear of that silken powder has already begun. And if this dust enters an engine, this is the result. Lost performance from a little dust, a little downtime that could be holding up other scheduled work, the costly man-hours of labor, the replacement parts, losses that could have and should have been prevented. That's why the primary element is so important. Here's how it works. The remaining dust from the pre-cleaner is removed as it travels through a replaceable paper cartridge. These pleats greatly increase its effective surface area. Frequently, a safety element is used in addition to the primary element. Its only function is to protect the engine if the primary element fails. However, because of its small size, it will clog rapidly. Never rely on the safety element to do the primary element's job. As dust is collected in the primary element, airflow to the engine is gradually restricted. This restriction indicator provides a visual indication that the filter element needs cleaning. Some restriction indicators actuate a warning light on the instrument panel to signal for servicing of the air cleaner. Dry element type air cleaners are growing in popularity because they're highly efficient, relatively small, lightweight, and because they can be mounted in any position. Now, let's discuss the oil bath cleaner. The oil bath air cleaner directs incoming air down through the center tube into the oil cup, then up through the filtering element and out to the intake manifold. Dust is trapped in the oil in both the cup and the filtering element. Dust in the filtering element is washed to the bottom of the cup. When the engine is running at slow speed, the oil is elevated only partway into the filter element. As the speed increases, it is elevated to its maximum. The oil bath cleaner is at maximum efficiency at rated engine speed only. The oil bath cleaner must be mounted in an upright position. If tilted too far, oil will be drawn into the engine. To clean an oil bath air cleaner, first remove the oil cup and pour the oil out. Then, clean the sediment from the bowl. If the fixed element becomes restricted and service is required, it must be removed. Clean it by soaking and flushing thoroughly in a solvent and blow it out with compressed air. Never use a steam cleaner. It will look clean on the surface, but instead of cleaning, the contaminants are driven deeper into the element. This creates a hidden sludge and restriction in the element's center. Inspect the center tube for any restrictions. Also, be sure there are no holes, loose joints, or restrictions in the ducting between the air cleaner and the intake manifold. Fill the oil cup exactly to the level line with the same quality and weight oil used in the engine. Never refill with used oil. Now, servicing the dry air cleaner. It's called for periodically in the operator's manual. Of course, the dustier the working environment, the more frequently inspection and service are required of the entire system. So let's talk about servicing the system, starting with the pre-cleaner. Some pre-cleaners have a clear plastic collecting bowl, so you can readily tell when it needs emptying. Allowing this pre-cleaner to become overloaded places a great burden on the primary element. If the dirt from the pre-cleaner is expelled by an unloader valve, the valve should be examined closely to make sure that dirt hasn't plugged the opening. Check for any tears or cracking and replace the valve if necessary. Some pre-cleaners have an aspirator which draws contaminants to the exhaust system, where they are expelled. This assembly needs occasional checking to assure that leaves or other debris aren't blocking the way. The aspirator consists of several spiral tubes called vortex generators installed in the air inlet. Notice that they protrude into the pre-cleaned air compartment. This compartment leads to the primary element. Air passing through the tubes is spun by the vortex generators, causing dirt particles to be thrown against the walls of the larger tubes and drawn off by the vacuum from the exhaust. Now, let's service the dry air cleaner. The heart of this air cleaner is its paper filter element. When it needs cleaning, follow the procedure outlined in the operator's manual. First, simply tap it with the hand while slowly rotating it. This will loosen the dust packed in the paper pleats. Never tap the filter on a hard surface. Here's what happens. The filter is so heavy with dust that banging it on a hard surface will break the paper element and allow dust to enter the engine. The second step is to blow out dust with compressed air. Direct, clean, dry air up and down the pleats, blowing from inside to outside. Use a low pressure, about 30 pounds per square inch. Keep dust from entering the inside of the element. For a completely thorough cleaning job, follow a third step. Use a non-sudsing detergent and soak the element. This step must be followed if the element is coated with soot. Never soak an element in fuel oil, gasoline, or solvent. Then use a tool such as this, designed to fit on the end of a water hose. Rinse from the inside out with clean water. Shake out the excess water and allow the element to air dry for at least 24 hours. Never install an element that is not completely dry. Moisture and dust form a muddy film on the element that restricts air movement. Following these steps, an element can be cleaned as many as 6 times before discarding. Many operators have a spare element to use while the other is being serviced. After checking for dents, nicks, or tears, check also for holes which could pass dust. Place a light bulb inside the element and look toward it from the outside. The smallest pinhole is reason enough to throw it away and install a new one. Finally, check the element seals to be sure they're reusable. Before reassembling the air cleaner, inspect the safety element in place for traces of dust. Unless there is evidence of a failure of the primary element, the safety element should not be removed except for its recommended annual replacement. At that time, don't attempt to clean it. Throw it away and install a new one. The air restriction indicator should be reset, if of the mechanical type, when the air cleaner is serviced. If the indicator doesn't work properly, replace it. Don't over-service a dry element air cleaner, only when the restriction indicator says to. Over-servicing exposes the induction system to possible contamination and the element to possible damage. If there's an occasion to disassemble the intake piping, check for evidence of dust entry at every point on the clean air side of the system. Every connection must be dust tight. The clean air side of the intake system should be checked regularly for leaks. If they should go undetected, serious damage will occur without prior warning. Beware of a damaged element, a loose or torn seal, improper element seating, loose connections or clamping at hose or pipe joints, hardened or cracked flexible connectors, cracked or worn spots in steel pipes, or a damaged or missing restriction indicator device. We've seen what happens on the clean air side of the system from undetected leaks or a failure of the air cleaner. Engine failures, a direct result of worn parts. But suppose the elements in pre-cleaner are doing their job. If you fail to service them, whenever servicing is indicated, the engine can still be damaged. As the particles begin to cause excessive restriction, a loss of power isn't immediately noticed particularly if the engine is turbocharged. However, fuel consumption will increase, demanding additional air from the turbocharger. There will be a dangerous rise in cylinder and exhaust temperatures. Oil consumption will occur. The result? Damage to piston, rings, valves, even the turbocharger itself. Repairs can cost plenty. Lost production due to downtime costs even more. Performance and power, designed and built into every engine. Proper preventive maintenance of the air induction system will assure clean air that engines may live to perform demanded applications. Every power plant has an optimum operating temperature to make best use of its power. We humans function best at 98.6 degrees Fahrenheit. Raise that temperature a degree or two, and performance falls off rapidly. So power plants need some sort of a cooling system. There's air cooling, and there's liquid cooling, which normally uses water as the major coolant source. Engines have the same problems with heat. Of the total fuel an engine burns to produce power, only about 1/3 of the heat can actually be used for power. What happens to the other 2/3 of the heat engines produce? About 1/3 goes out the exhaust, but the other 1/3 must be removed by the engine's cooling system if it's to operate properly. So the cooling system is an extremely important part of the engine. Kept clean and in good repair, it helps keep the engine operating at the proper temperature. The basic components of the cooling system are the radiator, pressure cap, the fan which draws air through the radiator, the water pump, coolant passages within the engine, the thermostat, and connecting hoses and pipes. Each of these components is designed to match the job it must perform. Together, they work as a balanced team to control and circulate the final basic component, the coolant, through the engine. The coolant and the cooling system are interrelated. The coolant must help maintain the cooling system components if the system is to accomplish its vital job of regulating engine temperature. At full load operation, flame temperatures in the engine's combustion chamber can go as high as 3,000 degrees Fahrenheit. The piston, liner, head gasket, valves, and injector, which are directly exposed to the heat of the combustion, would melt if it weren't for the cooling system. Heat is generated in the engine from the burning of fuel and from the continuous friction of the many fast-moving and close-fitting parts. The coolant circulates around and past high-temperature areas through passages in the engine. The heat is conducted through metal to the coolant, which flows to the radiator. There, the heat is dissipated to the air. So the cooling cycle is fire to metal to coolant to air. Simple enough, but very costly if the system and the coolant are not properly maintained. Let's review this in more detail. Rust occurs in the engine when water comes into contact with cast iron. While a good rust inhibitor will not rid an engine of existing rust, it will prevent rust in a new engine. Quality ethylene glycol antifreeze contains rust inhibitors in sufficient quantity to do the job. Mineral deposits occur when water with any mineral content comes in contact with hot metal. Water boiled in a tea kettle is a good example of this chemical reaction. This scale or deposit builds up on the metal and creates an insulation barrier that prevents heat from moving rapidly through the metal into the coolant. In fact, 1/48 of an inch of mineral buildup equals the same insulation characteristics as an additional inch of cast iron. The buildup on this liner equals 1.5 inches of cast iron. Chlorates prevent these mineral deposits. A good rust inhibitor contains sufficient chlorate to stop mineral buildup. Mineral deposits and rust damage the engine. Typically, they coat metal parts and cause hot spots. They wear out water pump bearings and seals and cause piston, ring, and liner failure, as well as failure of gaskets and packings. Mineral deposits and rust clog the oil cooler and radiator, and they reduce cooling efficiency significantly. Another culprit that causes clogging is oil and grease. This comes from leaking gaskets, poor servicing techniques, and pouring water into the radiator from an oily container. Remember that oil breaks down anti-rust and anti-mineral additives in the coolant. Water becomes acidic whenever metal dissolves in it. Seepage of head gaskets allows combustion gases to enter the coolant and increase its acidity. The acid then attacks all metal and rubber parts of the cooling system. If allowed to go unchecked, this chemical process accelerates and becomes a vicious cycle. Again, a good rust inhibitor will neutralize acid. The best insurance against rust, mineral deposits, and acid is an annual program of preventive maintenance of the cooling system. As we've mentioned before, rust inhibitors only keep the rust from forming. They don't get rid of it once it's in the system. So once a year, drain out and discard the old coolant. If the coolant drained out was rusty, use a good flushing agent to rid the system of rust. The system should be thoroughly flushed clean. In extremely stubborn cases, you may need to remove the radiator for chemical or mechanical cleaning. Now fill the radiator with clean, mineral-free water and antifreeze or a reputable rust inhibitor. If you have hard water in your area, purchase soft water for the system. It's relatively inexpensive, far less costly than the damage hard water can do. Never add water to a radiator that has been taken from a drainage ditch, irrigation canal, or similar source. Sediment from the water settles around the lower portion of coolant passages in the block. This prevents heat transfer from hot areas, such as the cylinder, and can result in costly repair. Use a good brand of ethylene glycol-based antifreeze. This is permanent antifreeze, which simply means that it won't boil away, not that it lasts forever. Add compatible inhibitors if necessary, but remember, most good antifreezes already contain them. Once the system is filled, it's essential to maintain coolant level high enough to prevent air from entering the system. Air is a good insulator, so it retards cooling. And since it contains oxygen, it accelerates rusting and corrosion. With the high volume of coolant flowing through the engine, small air bubbles want to stay entrapped in the system. Special baffling in the radiator top tank removes the bubbles from the system, and this is called de-aeration. Without sufficient water above the baffles, they cannot do their job. Coolant flows through the system with velocities high enough to give good heat transfer and with capacity high enough to carry the heat away, depending on radiator and water pump size. Coolant flow is between 1/2 and 3/4 gallon per minute per 1 horsepower at the engine flywheel. Therefore, an engine with 100 flywheel horsepower might have a total coolant flow of about 65 gallons per minute during full load operation. Maintaining the coolant assures the maximum life of all components of the cooling system. It's the one thing all these components have in common. But now, let's discuss the components in more detail. The radiator is where the coolant releases heat to the atmosphere. For the radiator to do its job properly, it must be kept clean, inside and out. The pressure cap has two functions. It allows pressurization of the system to raise the boiling point of the coolant. And it allows air to enter the system after engine shutdown. Each 1 pound of pressure per square inch will raise the boiling point of pure water 3 degrees Fahrenheit. So, as an example, a 7 psi radiator cap increases the water's boiling point by 21 degrees. Thus, a 7 psi radiator cap will raise the boiling point to 233 degrees at sea level. As the altitude increases, the boiling point is reduced. The pressure cap must be of correct specification for the system, and it must seal where it contacts the neck of the radiator to allow pressure buildup and prevent loss of coolant from the system. To check the radiator cap for correct opening pressure, use this special radiator cap tester. The fan's size, design, and RPM determine the volume of air moving through the radiator to remove heat. The fan depends on fan belt tension to maintain its optimum speed. The water pump is required to circulate many gallons of water through the engine and radiator every minute. In the case of belt-driven pumps, the belt must be correctly tensioned to assure peak efficiency. Connecting hoses should be checked periodically since they deteriorate with age. Usually the failure occurs inside the hose where it can't be seen. Even though a soft hose might appear normal on the outside, it may look like this on the inside. If it does, it will eventually collapse and restrict water flow at high water pump speed. Many engines are equipped with a crankcase oil cooler, which is a radiator-like core enclosed in a housing. Oil flows through one portion of the core, and coolant flows through another. This compounds the job of the cooling system, but fortunately, it's designed to handle this additional load. Many modern high-performance engines are equipped with turbochargers, and, for even more power, turbochargers with intercoolers. Oil that flows through the hot turbocharger must be cooled in the oil cooler. Since a turbocharged engine burns more fuel, there's more heat to be removed by the coolant. An intercooler is a radiator-like unit located in the intake manifold. Coolant circulates through its core and removes heat from the intake air that has been heated by the compression of the turbocharger. The result is still more work to be accomplished by the cooling system. As you would expect, it is designed accordingly. The thermostat is a heat-operated valve which controls coolant flow to maintain the correct engine operating temperature. During engine warm-up, the thermostat remains closed. This allows coolant to continually recirculate through the engine cooling passages without passing through the radiator. So, the engine warms up faster. During light engine load operation, the thermostat partially closes to prevent subnormal operating temperatures. This word of warning: never allow an engine to operate without its thermostat installed. Most engines have a normal operating temperature of at least 180 degrees Fahrenheit. When an engine runs below best operating temperature, fuel that hits the relatively cold combustion chamber or cylinder walls will not burn. This raw fuel dilutes the lube oil on cylinder walls and helps carry contaminants into the crankcase oil. This excess fuel also reduces the oil film thickness on the walls, which in turn allows faster wear of rings and liners and increased blow-by. This contamination results in stuck piston rings. Cold engine operation results in condensation in the crankcase, forming sludge in the oil, eventually resulting in failure of lubricated parts. This is especially true of pistons and crankshaft bearings. A properly functioning cooling system performs the critical task of removing heat from the engine. In turn, a properly conditioned coolant is the best way to maintain cooling system components for long, trouble-free life. Modern high-horsepower engines require more cooling power than ever. Proper preventive maintenance of the cooling system will contribute to top machine performance, everyone's goal. Efficient cooling systems that engines may live. Millions of years ago, nature structured thousands of hydrogen and carbon combinations to create crude oil. Modern man learned how to fraction these hydrocarbons into aromatics, naphthenes, and paraffins, and to further refine them into fuels and lubricating oils. These lubricating oils, so essential to internal combustion engines, are frequently misunderstood and misused. Yet their role is vital to engine power, performance, and reliability. With the low-powered engines of yesteryear, all we asked of an engine oil was lubrication to reduce friction and wear. But today's high-powered engines operate under heavier loads, faster speeds, at higher compression and temperatures, and moving parts are fit to much closer tolerances. We now know that what we traditionally refer to as lubricating oil actually serves four purposes: to lubricate, cool, seal, and clean. Anytime there is metal-to-metal contact between moving parts, scuffing, scoring, or wear is bound to occur. Wear also results from acid, corrosion, rusting, and abrasion caused by contaminants. So oil is required for lubrication. Engine oil must also help cool the engine. Heat is transferred through an oil film to the cylinder walls and cooling system. Heat is carried from the underside of the piston crown and skirt to the engine crankcase. Bearing temperatures are minimized by the oil to prevent failures. Piston rings alone cannot create a seal between the cylinder wall and the piston against the tremendous pressures of combustion. They depend on an oil film to create a seal, thus minimizing blow-by. During engine operation, deposits form on the piston and rings. These deposits include unburned and partially burned fuel, corrosive acids, dust and dirt, and water. The oil must remove these to prevent ring sticking and excessive wear. So oil is used for cleaning, lubricating, cooling, sealing, and cleaning. The four functions which engine oils must accomplish. Each is equally important. If any one of these functions is impaired, so are the other three, because these functions are interrelated. When the oil is accomplishing its four purposes equally, it's in balance. None of the functions has been stressed at the expense of another. Engine oil ratings and classifications are sometimes misunderstood, although they're of vital importance to the user. Best known, perhaps, is the Society of Automotive Engineers, or SAE classification, which measures the oil's viscosity, that is, its fluidity at a given temperature. Various additives are used to create multi-viscosity oils, which can be very useful during times of rapid and extreme temperature changes. Oil is further rated by API and military specifications. But the best way to decide what oil to use is to consult the operator's manual, where SAE weight and other ratings are clearly spelled out. Above all, buy quality. There is no such thing as cheap oil. The lower its quality, the more it costs in the long run. Oil contamination is inevitable. From the time new oil is poured in the crankcase, it immediately starts to become contaminated. The important thing is to drain the oil before it becomes saturated with contaminants and ceases to do its job. Carbon deposits form rapidly in the combustion chamber and find their way into the oil through blow-by, as well as through the oil's cleansing of the piston, land, and ring grooves. Water produced by combustion and condensation is a constant menace to efficient lubrication. Fuel dilution thins the oil. When water combines with the acidic content of partially burned fuel, it corrodes engine parts and enters the oil. The total result, sludge. It will foul piston rings, restrict and close oil passages, and ultimately lead to failure of the lubrication system and the engine. Sludge is an everyday occurrence in an improperly maintained crankcase. The use of inferior oils and the malfunction of fuel, air, and cooling systems also contribute to sludge formation. Overheating and overloading are also great sludge producers, and thus the obvious need to keep the crankcase oil maintained. Modern engines feature a full-flow pressurized oil system. It consists of the oil pan, the oil pump, the oil filter, and appropriate passages to direct oil to all moving parts. Some engines are also equipped with a crankcase oil cooler. Preventive maintenance of the lubrication system starts with selecting the best quality of oil available for the engine application, using the viscosity recommended in the operator's manual, constantly observing crankcase oil condition and maintaining the proper oil level. Does an engine burn oil? Most certainly. The piston rings meter a certain quantity of oil on the liner to properly lubricate pistons, rings, and liners. Normal temperatures within the engine result in oxidation of some of this oil. Remember the fuel, water, and acids that seep into the oil? They can replace the volume of oil that's been oxidized, thus causing the dipstick to read full and encouraging a false sense of security. The oil filter should be changed on a scheduled basis, at least as often as recommended in the operator's manual, more often if conditions demand. Remember, the operator's manual only states the maximum time the oil and filter should be used. Good judgment tells how often they should be serviced. Many full-flow filters have a special built-in bypass valve. When replacement is necessary, use only a genuine duplicate of the original filter. A quality filter has tremendous filtering capacity. Remember, the filter removes only solid contaminants from the oil. Liquid contaminants, such as water, acids, and coolants, will pass through the filter. Oil is formulated to keep them in solution rather than forming into a harmful sludge. So the color of the oil doesn't determine the need for change. If the oil is really doing its job of cleaning and keeping contaminants in suspension, the oil will appear to be dirty even after a few hours' use. This is properly formulated oil doing its job. Despite all the radio and television commercials to the contrary, don't use additives or dopes in the engine oil. Under the most ideal conditions, they might have a slight tendency to do the things claimed for them. But remember that the best oils are already balanced. They don't require any added phenomenal property. It is possible to upset the balance of the best oil by adding an additive. The best practice is to invest in quality oil and forget the dope. A modern top-quality oil with maximum metal wetting ability and detergent can safely be used to help clean up dirty engines. When adding such an oil to an exceptionally dirty engine, remember that the carbon, sludge, and other contaminants will probably overload the oil at first. This accumulation of filth will be rapid and must be drained from the engine when the oil shows signs of thickening. Don't expect to perform the first oil change in the maximum interval specified in the operator's manual. Observe the dipstick closely until the engine is clean. Many factors affect oil consumption. For instance, on naturally aspirated engines, a restricted air filter creates a higher negative pressure in the intake manifold. So the pistons draw oil from the engine crankcase in an attempt to pull in more air during the intake stroke. Worn valve guides also allow oil to be pulled into the cylinder. The piston rings are designed to distribute oil on the surface of the cylinder liner in exact amounts. Worn piston rings mean that more oil gets metered to the cylinder walls. Using the wrong oil, that is, an oil of the wrong viscosity or lacking the needed additives, can cause sticking rings. A sure way to spend lots of money is to buy cheap oil. Always allow the engine to sit a while before checking the dipstick for oil level. This permits the oil to drain into the crankcase. Since oil expands with heat, the best practice for checking oil level is to do it when the engine oil is at normal operating temperature and the engine has been shut down about 15 minutes. Avoid overfilling the crankcase. Oil should operate at temperatures above 150 degrees Fahrenheit. Cold engine operation permits excessive fuel dilution and acid formation. Preventive maintenance of the crankcase costs so little. The best oil, changed as frequently as recommended, more frequently if conditions require, and scheduled changing of the correct oil filter are the best investment you can make to avoid downtime and costly repair. With the fantastic productivity of today's machines, we can't afford lost job performance, let alone the costs incurred by labor and parts replacement. Lubricate, cool, seal, and clean. Those are the vital jobs performed by today's oil for today's modern engines. We go a long way for the fuels we burn in today's modern engines. Miles below ground, often miles below the sea as well. Of course, engines can't burn the crude in its raw form, so we refine it. And the better the refinery, the better job it does of removing the impurities that would otherwise contaminate our engines, especially dirt, water, and paraffin waxes. Now the fuel moves to regional storage and eventually the local distributor. From the refinery to on-site storage facilities, the quality of the fuel used depends on the quality of those who refined, transported, and stored it. This is what you buy in a brand name. It's the reason why it's so important to select a reputable source for all fuel requirements. When it comes to preventive maintenance of an engine's fuel system, cleanliness is the name of the game and can't be stressed too much. Cleanliness starts at the refinery, and once the fuel has been delivered, it's entirely up to you to maintain it. Whether we're talking diesel, gasoline, or LPG, all fuels have the same job to do: to ignite, produce heat, and by expanding gases, to generate power. Contaminants in the fuel can reduce that power considerably and frequently cause costly engine damage as well. When reference is made to a specific gasoline's octane rating, it is simply a measurement of that gasoline's ability to resist knocking. By using additives and through modern refining techniques, the octane rating is controlled to permit the gasoline to burn slowly and evenly in a high compression engine. A gasoline with too low an octane rating for the engine will ignite in an explosive manner, producing a damaging knock. The operator's manual specifies the minimum octane rating permissible. In almost all cases, this rating permits the use of regular grade fuel. While premium grade, that is higher octane fuels, are usable, they offer no advantage unless the manual specifies their use. In the case of diesel fuel, just the opposite property is desired. The cetane number of a specific diesel fuel refers to its ability to produce fast, spontaneous combustion. This combustion is controlled by the rate of fuel injection. But a diesel fuel cetane number is only one of many properties to be considered. Two major grade classifications are most often recommended for high-speed diesels. They are grades 1D and 2D. The owner's manual specifies their use and should be followed accordingly. In any case, never burn furnace fuel in a high-speed diesel engine. Furnace oil contains more of the heavy cracked distillates, such as wax. It can rapidly clog the fuel system, and in cold weather, it thickens and may not flow through the system, as shown here on the left. It can make engine starting virtually impossible. On the right, diesel fuel flows freely. Remember, refineries do not attempt to supply dealers with a fuel oil that's suitable for both diesel engines and heating a home. Once you've selected the right fuel from a reputable dealer, it's important to maintain that quality. Keep the fuel free of harmful contaminants and condensation when the fuel is being pumped into an on-site storage tank. If there is any water present, the water mixes with fuel in small droplets. The tank is tilted slightly to collect water at the low end and away from the hose. This water will settle to the bottom in about 24 hours. The water should be drained at the rear of the tank periodically. The hose should have a filter to further separate water and other impurities. As you can see in this demonstration, water settles out of gasoline far more rapidly than it does from diesel fuel. Therefore, allow a newly delivered tank full of diesel fuel at least 24 hours for water to settle before using. The best practice is to use 2 storage tanks. Never store diesel fuel in a tank that has previously been used for gasoline storage. Over a period of time, various contaminants in gasoline, shown here in these vials, settle to the bottom and build up on the inside walls of the tank. Diesel fuel loosens this accumulation, which then floats in suspension. Diesel fuel also reacts with galvanized metal, so it shouldn't be stored in a galvanized tank, since the subsequent corrosion will clog the engine fuel system. Diesel and gasoline is stored and handled much the same. They're subject to heat absorption and evaporation losses. By storing in a light color tank that's well shaded and equipped with a pressure vacuum relief valve, evaporation losses can be drastically reduced. The filler hose nozzle should be properly cared for. Be sure the nozzle is clean. Before inserting the nozzle in the fuel tank, it's good practice to shoot a bit of fuel through the nozzle to flush water or any other contaminant from the nozzle. We strongly recommend a filter between the tank and the hose. And of course, store the nozzle downward with a cover on it when not in use. Here is one of the greatest potential sources of fuel contamination: the portable tank that is taken to the job site. Whatever its size, all the care exercised in on-site storage is wasted if the portable container is contaminated. Remember that the quality of the fuel in the engine supply tank is only as good as the cleanliness of that portable tank. LP gas must also be purchased from a reputable dealer to make sure that contamination in the storage tank is minimal. In addition to other contaminants, LPG contains propylene, a sticky substance that tends to gum up the engine fuel system. A fuel filter is located between the LPG engine supply tank and the converter. Should the filter become clogged, the restriction will cause the filter to accumulate frost with the engine running. A typical diesel engine fuel system has a fuel storage tank, a fuel transfer pump, a single or dual fuel filter, an injection pump, injection nozzles, and connecting lines. The transfer pump draws fuel from the engine supply tank. Whatever the tank capacity, size, and shape, it must be vented to allow air to enter and replace the fuel used. The filler cap should always be wiped clean of dust and dirt before removing it for refueling. The engine supply tank is equipped with a water drain. This drain should be checked periodically for water that might accumulate from condensation. Modern diesel engines have a fuel transfer pump, which supplies sufficient pressure to move the fuel through the filters. The pump usually has a hand primer lever for bleeding air from the system. This pump also contains a fuel strainer. Fuel filtration is very important in a diesel engine because injection parts are precision made to extremely fine tolerances. These precision parts must be protected from the most minute abrasives. In this dual series type filter, the fuel passes through a first stage element, then it passes through the second stage element. This element is designed to trap and reveal water that comes from poorly maintained fuel. There are other types of filters, such as these. The fuel from the filter moves under moderate pressure to the injection pump. They vary in makes and models, but their purpose is the same. Injection pressures will be as high as 5,000 to 10,000 psi at the time of injection. Spring pressure holds the injection nozzle closed until just the right instant, when the high pressure forces it open to inject the fuel. The timing of injection is extremely critical, just as the timing of a spark in a spark ignition engine. The diesel nozzle must inject the precise quantity of fuel in a spray or atomized form. Some injectors have a fuel filter built in, which can filter out foreign particles as small as 1 micron. Just for comparison, a particle 1 micron in size equals 1/100th of an average human hair. This suggests the fact that even extremely small impurities in diesel fuel can be very injurious to precision injection parts. Whenever diesel or gasoline-powered machines have been idle for any length of time, it's wise to check the fuel tank drain for water and sediment. If a gasoline engine is to be stored for a long period, drain the gasoline tank and carburetor. On the other hand, a diesel engine should be stored with the system full. Use this engine storage preservative and add to the diesel fuel system as directed. Always refuel the equipment at the end of the work period. This minimizes condensation in the tank, and it assures a full fuel tank at the start of the next work period. Of course, the fuel cap should be wiped clean, just like the fuel hose nozzle. Some fuel systems are equipped with a sediment bowl on the fuel pump. This bowl should be removed and cleaned periodically. Fuel filter elements should be replaced as specified in the operator's manual. Before removing the filter during service, clean the entire filter area of dust and grime. Otherwise, these impurities will be washed into the injection system, and severe damage could result. If you find that it's frequently necessary to change the fuel filter, don't blame the filter. The fact that it's loading up with impurities is proof that it's doing the job it was intended to do. As you can see, it has plenty of filter area to trap contaminants. So filters that clog too soon indicate that the fuel being supplied is contaminated. To eliminate contamination, clean the engine supply tank. Check and clean storage tanks as necessary. Also, check the fuel supplier. When the fuel filter is replaced, use a factory-authorized filter element. Will fits may appear to last longer, but in reality, they're seldom designed to remove as much contamination from the fuel. Eventual damage is the ultimate result. When the fuel filter is removed, or whenever the machine runs out of fuel, air should be bled from the fuel system. The operator's manual specifies this procedure. If the engine still misses after bleeding the filter and will not smooth out, the entire fuel system should be bled. Anytime you suspect problems in the injection system, be sure to have it inspected. Otherwise, the consequences can be drastic. For example, when contaminants enter the injection pump, they wear away the finely fitted parts and result in expensive damage. Clogged nozzles can create enough pressure to cause total pump failure. Also, they can have distorted spray patterns that spray first on cylinder liners and wash away lubrication. A distorted spray pattern can result in damage to the piston and rings. Careless fuel storage or negligence in replacing an inexpensive fuel filter can thus result in hundreds of dollars in repair costs, often thousands of dollars lost when downtime prevents a machine from performing when it's needed. Remember, when it comes to the fuel system of today's high-performance engines, the name of the game is cleanliness. That's the way to get all the power possible from every drop of fuel in today's high-performance engine.